basically, how this week is going to work, right? Um, is we're going to focus on T-beams and design steps. So I know I've talked about T-beams like slightly, like theoretically, I guess, um, so far, but now we're going to be doing like an actual design of them. But first, we'll run over a bit more theory. Basically, there's some terms which I've only briefly alluded to, like effective width, in terms of like the flange width for the T-beam in a slab system,
Mhm.
and um, yeah, and like cover stuff like that. We'll run over a bit more, and then basically we're gonna start moving into design. So the only thing that we've really talked about, which is design centric so far, is how M star, or let's just say W star, has been calculated using these kind of load combinations. Is everyone in agreement to this? Yeah, we've kind of dealt with that the last few weeks, right?
Yeah.
Um, so basically, we're gonna dive more into design, and specifically, if you've done steels, right? Let me just run through how steels worked. Um, Say you're doing tension design in steel. What happens is you calculate the external axial load being taken by the steel member, and it has to be less than your ultimate in strength design, in your ultimate tensile axial force, right? And basically, you went onto this website called One Steel, and you can select from a variety of I-beams, for example, and those have like specified dimensions, whatever, like widths, depths, stuff like that, and they'll have all these properties which you calculate, like Ag, all that stuff, like area. You chuck it into the formulas for your capacity, and you check whether it passes some test, and if it does, then that's all good, right? That's what sizing a steel member is all about, right? But today we're going to be sizing concrete members. So let me just quickly delete that. We're going to be sizing concrete members. So like, for example, if it's a rectangular member, right, we're going to be asking the question of, okay, how deep is this concrete member? How wide is this concrete member? What's our area of tensile steel? What's our area of compressive steel? Actually, that's not part of flexural design, so at least in this course. So we just care about the tensile steel, right? But what is part of the course is designing T-beams, which you can imagine gets pretty cooked, considering we don't know what the depth of it is, or the width here, right? Let's call it BW. Okay. Does anyone have any questions right now?
No, not so far.
Okay. Yeah. Okay. But basically, my plan is, instead of running through the design steps, because honestly, there's quite a few steps. What I'll get you guys to do later, and why I sent you the Google Drive link, is you can pull up the design steps when we get up to doing the workshop questions, and this is going to be a blank page on my end, and you guys will help me run through how to design this T-beam given my instructions in the design steps. So it'll be similar to having like a cheat sheet for a finals question, and obviously, like, you're all there to help each other, and there's no problem if what you're saying is wrong. But I just wanted you to have a bit more of an interactive experience than me just like yelling at you,
Mhm.
yapping at you, basically, right? But for the first little bit, I'm gonna be yapping, alright? So, um, got Minecraft up again, right? You remember this from before? This was
Mhm.
our slab and beam floor system, yeah. And okay, let's just quickly iron out some terms. So we've talked about the T beam and why, um, I guess like it is a T beam. It's because the beam absorbs a little bit of the sides from the slab system, right? And we've talked about something, I think I might have called it a flangeral beam by accident. I realized in the recording, but it's called a spandrel beam, I think. It just means like an edge beam, right? These are also called L beams in the standards. right? Because it's an L, but it's like rotated. You know what I mean? Tetris block kind of thing, right? So yeah. I'll just go into my little cross section of them, right? So there's a couple of things to point out here. So like in terms of the lingo, or sorry, where everything is placed, our shear bars or our shear reinforcement is kind of like that that loop thing that goes over our axial bars, right? And our axial reinforcements are both the tensile and compressive steel. I've just called them axial because technically it depends on where the whether the moment is sagging or hogging, or like whether it's a positive or negative moment, right? For whether these kind of axial bars are going to be taking on tension or compression. Does everyone know what I'm talking about when I say that?
Mm-hmm.
So let's just draw like a continuous beam, for example.
Can you say that again?
Yeah, that's right. Okay, all good. So we have areas in a continuous beam where we have positive and negative moments, right? Where there's a negative moment, this is called hogging. This is the consultant lingo, Dom, essentially. And then these areas of positive moment are called sagging, right? So Dom, if you just want to have a crack at this, like this bottom layer of steel, would this, in the case of sagging, is this going to be tensile or compressive?
Tensile?
Yes, and so therefore these are the compressive ones, right? Because
Yep.
on the compressive side. What about the other way around, the hogging moments? What will be the bottom layer?
Compressive.
Yes, very good. And then the top becomes a tensile, yeah.
Yep.
That's all you really need to know. So it depends on what kind of moments are being experienced along the beam. And what, yeah, anyway. So I just called them axial reinforcements, right?
Yep.
There's a couple of dimensions I'll draw on the left-hand side. And yeah, basically, I've alluded to this one a few times, but we have something called the effective width, and that is talking about the flange width for this L-beam in particular, right? I've included the L-beam just because it's in the code, but to be honest, I've never seen an L-beam in this course. I've only seen the T-beams, right? So you're never really going to be designing an L-beam, and I think part of the reason for that is because it's in terms of like its X direction centroid, it's off-center, right? They don't want you to really deal with those off-center kind of effects, so you'll probably be more likely designing a T-beam, right? But I'll just show you it anyway. This is part of the slab, so we call this DS. This is the depth of the slab. That's like one dimension to keep in mind. Another dimension here is the overall depth, right? So we just call that D, right? Another dimension I want to point out as well is, what would we, Josh, if you want to have a crack at this. Sorry, just because it's online, I can't really like look at people, so I'm just gonna pick on people.
Okay.
What do you reckon this is called? What I've called it BW, but what do you reckon that is?
It's the width of, well, it's the width of the bottom part, right? It's not the entire thing. So
yes.
Is it the width of web?
Yes. So W standing for web. That again, these are all terms I want you guys to get familiar with. But yeah, you're essentially right there, Josh. It's differentiated because it's just the bottom part, but we call it the web. So we call this top part the flange, and
flange, and then the bottom.
Yeah, but it's this naming notation is because of the width dimension. It's not because of where it's positioned. So the flange part of a cross section is always the wider part, and the less wide part is always called the web.
Okay.
Do you know what I mean? So on an I-beam, they've learned this in steels in third year. You have two flanges. Yeah, you have two flanges and one web. Do you know what I mean? So that's where
Yeah.
the language comes in. Okay. And for a T-beam, we also have that whole area called the effective width, like this, right? But it's now we have like a symmetrical kind of shape because it takes an equal amount of concrete from both sides of the slab, right? Does that make sense? Yeah.
Yes.
I'm gonna take a little like kind of zoom in of this corner here just to explain the concept of cover. So I've zoomed in, I've redrawn it. What we say is that from the center of the axial bar to the outer edge, that we call that the cover, right? And we call the distance from the edge of the outer edge of the shear bar to the outer edge, we call that the clear cover, right? So you can see how this formula plays in because we have to consider the radius of the axial bar, but an entire diameter worth of the shear bar. And what we do in this topic in particular, by the way, where we are is this is what's covered in the first half of week 7, which is why I'm doing it in this yap right now. These are the design steps for flexure. But what I want to focus on in week 7 instead is shear design, which is something completely new, right? So I don't want to confuse you guys, and I've only got an hour, you know what I mean, like in week 7. So we're still kind of talking about the same things that we have been for the last 2 weeks, particularly in week 5. But there's just more in this topic to talk about. Yeah, like when we're designing a custom section. So yeah, anyway, we consider the cover to be 65 millimeters as a designer value. So there's going to be a lot of designer values coming out in this week, and that's just another way of saying purely based off of feelings. Like there's going to be a bunch of numbers which come out purely based off of feelings, and they're generally right. So this is one of those feelings numbers. This isn't anywhere in the standards. Okay, but it is like recommended in Taewan's like lecture slides and stuff, right? Okay. So we can determine the effective width, right? So let's just take this T-beam, that dimension, right, for example. And it's a simple formula, which is talking about the web width, and then a portion of A. So A is what we call the flexural span, right? Does anyone want to have a crack at what flexural span is? I'm gonna pick on Justin. Sorry.
Well, I guess what is flexural span the length between the beam and the clear cover?
Oh, I know what you mean. Do you mean like column kind of thing? So from the beam and that, or
Yeah.
Oh.
Well, I was actually thinking also the whole length, but I didn't really know.
Oh, this is the clear span, right? You're talking about this?
Yeah.
Okay. We call
No.
that the clear span, right? So between the columns and all that. Okay. Yeah,
Okay.
sorry, I kind of gave you a stitch up question. It's kind of a hard question. But in a continuous beam, let's just see it on the next page. Okay. Basically, on a continuous beam, right, like this, a flexural span is basically the distance between where there's 0 moments, right? You see how there's 0 moments here and 0 moments here? That's the part which is in positive bending. Do you know what I mean?
Yeah.
And for a simply supported beam with rigid connections like this column, this is approximately equal to just the regular span.
Okay. Cool.
Yeah. So anyway, I think you guys get it just from the visualization. Is anyone confused or not sure about that? Just keep in mind, it's kind of not intuitive, but the width of this web is actually a function of A, which goes in the other dimension. Do you know what I mean? It goes in the long ways dimension. So that's what might originally seem a bit unintuitive, but yeah, someone who was smart figured that out, basically. Another thing to keep in mind, this is from the workshop solutions, is that for the middle of this continuous beam, so we're talking about the middle span, like an interior span, there's actually a higher bending moment as a hogging moment at the supports than for the mid span, which is positive sagging moment, right? Like the magnitude is bigger. That's just a little fun fact, to be honest. It won't really come up in the course, but the shape of the bending moment diagram will look something like that. Yeah. Does anyone have any questions? So we're actually going to do one of these questions later that relates to the continuous beam, and it's going to be a T-beam. And we're going to be calculating the mid moment, basically. Okay. So basically now I'm going to move on to design a handbook. So this is just fucking Stephen Foster's biggest fan. This book is sometimes called, just abbreviated to FKW. That's for the authors' names. And it's just recommended designer values that aren't explicitly in AS3600. These are vibes-based values for sectioning like concrete and making like a section that's like appropriately sized, right, based on the loading. So some numbers to keep in mind that you'll see come up is they'll give you an initial depth value, which I've called D here. I feel like this number is more common. So you basically take the clear span and divide it by 10, because you're usually given the span, right? But in this course, I haven't seen anyone care about the column width itself, right? So the difference between clear span's here, right? And center to center span is between the middle of the columns, right? But you're never really given the column widths like here, right? Or the column, I guess, radius, if you want to call it that. So it's the same number. We take L and Ln in this course together. Yeah. Okay. Does anyone have any questions to do with that?
I'm good.
Okay, bet. The next one is the web width, right? So this is just written in the notes as B, but for a T-beam, right, we have two Bs, right? We have BW and we have BEF.
Yes, yeah.
Yeah, the flange width, right? So we're just talking about BW for this value for B if we're designing a T-beam, right? And you know, in the workshop examples, there's basically 3 questions to do with flexural design, and question 1, you don't design the concrete, you just design the steel, right? Like how much steel you need. In question 2, they take the value, the initial guess is 0.7 D. Sorry, I'm getting a bit of background. I'm getting a bit of noise from someone in Discord. Just check that, please. Yeah, and then question 3, it takes it as 0.5 D. So I can't tell you which one's the right guess, to be honest. You just have to. Sometimes you look at the solutions and be like, how the fuck did they like decide this, right? It's because there's more than one right answer, right? If you think about.
So like when you design and you do initial sizing,
Yep.
do you have to do it like steels where you have to do multiple guesses and then design each of them and just test it out, or how does that work?
Yeah, I know what you mean. So for reference for the second years and like all that, looking at this, right? Okay, let's take N as an example. So this is tension design in steel. It's the first thing you learn. It's the most straightforward one, right? What it's saying is there's a certain amount of tension that it can take. For example, 400 kilonewtons, right? Where it's being pulled apart, and then we basically have to choose a universal beam which fits this amount of loading, right? Keeping in mind some capacity reduction factor, right? So once you do all the calcs and all that, you might find that this value on the right hand side is something like 390 kilonewtons. Well, then it doesn't pass the check, so you have to redo your calculation, right? That means you're under engineering it and it's not safe, right? The other thing that might happen is you might oversize it by too much. Say you oversize it and it's 550 kilonewtons on the right hand side, and you're wasting a lot of material, right? So essentially you're trying to edge it to be within an acceptable amount of margin over, so that it's safe but not over engineered and wasting materials. That's what this whole like capacity checks is kind of for, right? And if it passes this, it's considered designed correctly to AS 3600, right? So the idea, I think, that you're mentioning, Dom, is that you have to do it multiple times if your number's wrong. But what I'm trying to say is there's more than one correct answer, and your initial guess will change things, but not by much, if that makes sense. So like, I guess if you want to be a bit more conservative, you go for if you want to be a bit more generous with your section size, you go for a bigger width, if you know what I mean. And so you'll always go and waste materials by over designing it rather than under designing it and resulting in an unsafe structure. Because if you end up with an unsafe structure, you can't continue in the exam. Do you know what I mean? Like like if it fails the capacity reduction check, you have to redo it until it fucking works, if that makes sense. But if it's over engineered by a bit, I think you can continue, to be honest, and it's not the biggest deal.
Okay, yep.
So yeah, like you can, if it's fucking like 300, you have to redo the question. If it's like 500, honestly, I think in an exam setting, I would just move on. If it's 700, I think you have to redo it, to be honest. That's like a bit too unacceptable.
Oh, okay.
So yeah.
Wait, what's the accepted percentage margin?
I can't give you a straight answer to that. It's based on feelings. All these designer values are based on feelings.
Okay, I love the consultant like nature of this.
Mate, I would say try to aim for no more than like 30% over, right? So 50% over would be 600, right? Yeah, try to aim for like 500-ish in this case. Yeah. Then I would say it's acceptable. Okay. All right. Another thing after initial section sizing you'll see in the steps is loading, right? So tributary width, right? Did you have to do this in steels? Can one of the third years inform me on this?
I remember it being thrown around, so I'm pretty sure, but I've forgotten it.
Yeah, that's all good. Dumbass. No, no, but basically it looks like this. So if we have a slab system that looks like this, right? Where that's our T-beam and that's our L-beam, right? The idea is that all these loads, right, so there'll be some live loading on it, right? So pretend there's a uniformly distributed load over the entire thing. I just will rub it out. And the self-weight of the concrete. These are all like loads which are happening on this slab beam system, right? The idea is that the loads have to go somewhere, okay? And so they transfer from the slab to the beam, and they kind of transfer to the path of least resistance, right? So it kind of goes like this. That makes sense. Just think of it like every fucking electron has to be accounted for in terms of the self-weight and the loading. So for the L-beam, what this means is that it will take this much tributary area in terms of its like the loads it's going to absorb, and for a T-beam it's going to take effectively twice as much because it's going to take it from both sides, right? Whereas L-beam's only going to be taking loads from one side, right? So does someone want to give a crack at what determines this? Like, how do we determine, say, this is called the tributary width. What determines the tributary width here? It's
I remember.
Distance
Yeah.
between columns.
Very good. Very, very good. Okay, so I'm going to scroll up because this is actually something which I skipped over. So for an L-beam, we call this center to center spacing divided by 2. And for our T-beam, it's simply center to center spacing. Right?
Oh, I remember Hamid did this. Yeah. Okay.
So center to center spacing is here to here, right? We literally just shift the whole thing over and it ends up being in the middle of between where the columns are, if that makes sense.
Voila.
Well, indeed. We continue. Okay. So yeah, that's this here. Yeah. Okay. So basically, when we're trying to size our section, we start with these initial guess values, and we actually have to calculate M star. You'll see in a bit. You have to calculate M star, and you determine the loading, like W and all that, and you plug it into M star, and then from this, we essentially have I haven't really shown you the formula, so I can't explain this too hard, but essentially there's a resizing formula of some sort, and then there's some assumptions which goes into it. So essentially this is to do with the cover. Sorry, okay, I have to explain what effective depth is, right? So effective depth is from the compressive layer to the centroid of the tensile fibers. So if we have 2 layers of tensile fibers, where do you reckon this is?
I'm gonna give it a guess between the 2 tensile bars.
Very good, perfect. So it's not at the outer layer or the inner layer, it's in the middle. Perfect. And of course, if you have 3 layers, it's in the middle of the middle layer, right? Okay, so basically at this stage we set B equal to 0.5 D. This is another designer vibe value basically. And sometimes and if we're being like physically accurate, it's the width of the compressive side of the T-beam. But luckily we don't have to think about that because in this I guess I don't know if this is in the standards, but it's in Talon's notes. We always take this as B web to be conservative. Yeah, so you won't have to think about which side is which for this formula. It's just BW basically. Okay, the other thing we have to assume is we have a KU of 0.25, except in question 3 it tells you a slightly different KU value, but that's fine. Does anyone remember what KU is about? So KU is a measure of ductility, and essentially the lower this number is, the more ductile it is, which is good because we want a ductile failure essentially.
Oh yeah, so like it shouldn't be brittle.
Yes. So if our ratio of DN to DO is too high, it means that the concrete is going to crack before it's not about concrete cracking. It's about the concrete's going to reach ultimate compressive strain before the steel yields, which isn't good. Because if the steel yields first, right, that's what we call a ductile failure, right? It's really hard to explain this concept because it's not really another like analogy that I could think of. Okay, basically your steel acts a bit like Play-Doh, right? and when you pull Play-Doh apart, it's gonna stretch a bit, right? But if
Yep.
you put this Play-Doh in like, I don't know, if you put this Play-Doh inside something that behaves like ceramic or like a like in concrete, right? If the concrete like completely fails first, it's not good because the whole like the Play-Doh is gonna break brutally, essentially, right? But if the Play-Doh
Yep.
yields first, it's gonna provide a bit of that like yielding strength. Okay, this analogy is starting to break apart, but hopefully you get what I mean. You want the steel to yield before the concrete, essentially, and it's to do with how low this ratio is.
Is this the concept that you were saying where you want the concrete to show signs of cracking first before it breaks? Or not quite?
Yeah, I mean, it's to do with that. But actually, like on a deeper level, it's like when it's a composite section, that only happens because the steel is there and the steel yields first. Because if you have concrete that's not reinforced, right, it cracks and that crack propagates and is exponential in terms of how much it'll essentially break straight away, right? Once it starts to crack, it's essentially as good as gone. But if you have steel there as well, the cracking is like a visual sign of the steel yielding.
Okay, gotcha.
Yeah.
Oh, right.
Yeah. Because anyway, it either goes from uncracked to completely fucked straight away if it's unreinforced, or the cracking is a good sign that the steel is doing its job properly.
Okay. That means that the steel's failed, that means the concrete is taking on more load, that means that is starting to break. Is that the kind of logic?
Wait, say that again, sorry.
So ideally the steel it begins to fail, right? So that the concrete has to take on more of that load, and then it starts to crack, and then
yes,
that shows us. Okay.
It's not that the steel is taking on any less of the forces, though. To be honest, right? What steel does is once steel yields, it reaches its maximum power, and it stays at that power.
Yes.
That's what we call Fy, the yield strength.
Okay.
So if the steel yields, it just means the steel's at ultimate power. Like, not ultimate, that's a bad word to use. It's at the highest power it's gonna be at, which is good because it's doing its job properly. All whilst the concrete's doing its thing the whole time.
Okay, so that's edging it a little bit.
Yeah. Okay.
Gotcha.
Whatever helps you sleep at night, basically.
Okay.
You can think of it like that, yeah, sure.
Yeah.
And we know that in ductile failure, the phi value can not oscillate, but it can range between 0.65 and 0.85. But obviously when we're designing a section, we want it to be designed to be ductile, right? Like we're not aiming for a brittle failure of 0.65. So that's why we set this Ku value comfortably below 0.36 so that we can design a ductile section. Does that make sense, everyone? And same thing, this is a vibe value. The cover will be 65 mil. Okay, so for this next part, we're going to switch gears a little bit. You guys are going to tell me what to do, right? Actually, Josh, if you can record that thing, like your screen.
Sounds good. We'll do.
Basically, pull up the PDF, and we'll work through all these steps, step by step, essentially. And you tell me what to do next, okay? And I'm just going to show you the question. So this question reads: a reinforced concrete slab and beam floor system has a slab with overall depth 180 mil, supported by T-beams at 6 meter centers. The beams are simply supported over a span of 8 meters, a flexural span of 7.4 meters. The floor is to carry a live load of 3 kPa, and the dead load is soft weight only. Design longitudinal reinforcement, which is just another way of saying axial, at the mid-span of the beam. That will make a big difference, whether we're designing for the mid-span or the support. And then it gives you a bunch of values, essentially, right? Okay, so I need you guys to kind of discuss here a little bit. What should we do first?
So you got your concrete, like your density and all that stuff.
Yes.
Would it be
weight
the-
And then-
25. Okay, good.
Oh, it's already provided. Oh, it's-
No, that's good though. That's where we're heading. So what is the density or unit weight? What does that contribute towards? Let's back work it.
self-weight, dead load.
Yeah, self weight, G, dead load, good. Okay, but how do we convert it from? Because normally we want dead load in kilonewtons per meter, right? So what do we need to do to convert it to dead load?
The area.
Yeah, good. How do we get the area?
Your concrete beam, like there's your length and your width of that.
The flex.
So the
So
span of
the
80 meters.
length and the width. Just be careful with the language here. The length refers to the beam direction, right? The span.
Yeah.
You're talking about the width and the depth.
Yeah.
Someone help her out here. What are we designing?
Oh, do you mean the cross section? Into the cross section.
Yes. But what
The
type of
cross-section,
cross-section
okay.
are we?
So the depth and then the width.
So are we designing a rectangular section?
Yeah.
Nope.
The area of the rectangle cross section.
Incorrect. We're designing a T-beam.
Oh, the T section.
Yep. Okay. So how do we get this area? Would you say?
Okay. To find the area.
Yeah.
Well, can we label the diagram first? So,
The depth, the 180 plus the whole length of like from the top to the bottom.
wait, surely that can't be 180. That's millimeters, is it?
No. You're on the right track, Justin. The depth of that you're reading in the question is the depth of just the slab, which is that top part, right? So it's the
Yes.
depth of that flange. I'll give you a hint. It's the first step in design steps. wait.
So then D.
Yeah, D and BW, right? We have to guess these values, right?
Yeah.
Oh my fucking god.
But then D is already given, right? With 180. So are we just
Incorrect.
guessing BW?
We're not given D. So big D is the overall depth. Previous
So
page.
big D is ln on, so clear span divided by 10.
Very good.
Okay,
So what would that be?
so I want to say 8 meters, but that's probably not right, is it?
It is right.
8 meters.
It is correct.
Okay.
It says
Okay,
the beams
okay.
are supported over a span of 8 meters, which implies that it's it implies this, right? That this is 8 meters, right?
Right.
But we're not given what the column widths are, so effectively LN and L are the same thing.
Okay.
So it doesn't matter.
Oh.
It is 8 meters, right?
Okay.
But are we
8
getting
meters.
8 divided by 10?
Yeah, so 0.8.
8, so 0.8 what?
Why is it just
Wait, 0.8.
meters?
Meters.
It's 0.8 meters, right? But how does that translate to a cross section? Because in a cross section we don't use meters, we use millimeters, right?
Oh, so 800 mil.
Times 5,000.
Yeah, so that actually seems right now, right? 800 mil. That's our initial.
Oh,
Okay, what about BW, the web width?
so there as well.
BW is that just 0.5 to 0.8 D?
Oh yeah. Just because I've seen the solutions, they say 0.7 D, so that we can.
Is there a way to actually figure out which value we multiply by D?
That's what I was saying. It's purely based on feelings. So I
Oh,
can't tell you. I
okay.
can only give you examples of what they did. So in question 2, which is this question, they do 0.7 D. But in question 3, they do 0.5 D. So you really pick your poison. I'm not too sure. Like,
Okay.
I would just do 0.7 because it's safer. It designs a bigger section, and so you'll always go over the capacity check rather than under.
560, is it?
Yep. So we've effectively figured out what this area will be once we multiply everything together, right?
Yeah. Do we do loading? So tributary one?
But we don't know what. Yeah. So here we're not actually designing the flange width right now. We're designing the tributary width to determine the loading, right?
Yeah.
So what's the tributary width? So this is the thing I just
So-
told you earlier.
It's the center to center spacing,
Yep.
which is it? Do we take it as 8 meters in this case? Oh wait, yeah. Do we take it as 8
That's
meters?
the span, right? So that's
Yeah.
the span is the lengthways direction.
Yeah.
But we're talking about, if I go over to my Minecraft drawing, we care about the other way.
6 meters.
Very good. So we don't care about the span direction. We care about this center to center spacing of the columns. Good job, Sissy. It's 6 meters there. It says the T beams are at 6 meter centers.
Okay, now I'm getting confused about which kind of axis we're looking at, or what direction we're looking from.
So we're looking at the cross section, and the cross section looks like this. That's my eye looking at it. It looks like this. It should be drawn more like this if it's center to center. Right.
Wait, can you show that on the Minecraft thing? So is that going into the page on the Minecraft?
Okay, basically here is the lengthways direction, but
Okay.
if I'm looking at it from here, we're looking at what I've drawn in blue here. This is center to center spacing, right?
Yeah.
The columns. Whereas the beams, which are simply supported, go this way. I mean, sorry, they're not simply supported. In this case, it's a continuous beam.
Oh, okay.
Does that make sense? And then the bending moment diagram looked like this. Going that way. So we're looking at how far the beams are from each other. Does that make sense? Rather than how long the beam is.
Okay, yeah, I got that. Okay, that makes sense. Actually, makes a lot of sense.
The Minecraft drawing's OP.
Yeah.
Okay, so they're at 6 meter centers, right? Which means that they're again, this is how far the beams are apart. Yeah. So this is 6,000 for a T-beam. Yes. Okay, so how do we get WG? So area, I'm gonna skip all the calcs and shit. Yeah, so we know this, right? We know 25 is the unit weight, and we know the area, it's this, right? Yeah? When we multiply that together, WG gives us 35.68 kilonewtons per meter, right? All good?
Yes.
Okay, what about WQ? What about the live load? So the live load, let's do it in purple. It said to be 3 kPa. So what's kPa? What does that unit mean?
Kilonewton per square meter?
Yes. So in terms of that Minecraft drawing again. Oh, maybe I'll just do this drawing. Do you see how blue is kind of like a distributed load over a 2D area?
Yeah.
That's what kPa is essentially, right? So we need to convert it into per meter run, right? So let me I might just spill the beans on how to do this. Let me draw I actually drew the T-beam like kind of out of scale because we're drawing it according to the tributary area, not the actual flange width, because we just care about the external loads right now. It looks more like this. Right, that's WQ right there. Right, and we've established that this is 6 meters, right? Right, and we know that that Q is 3 kPa, right? Are we following? So to get it into a one-dimensional thing, we literally just multiply that tributary width by 3 kPa. So instead of kPa, I'm going to write kilonewtons per meter squared, right? Just to make it a bit more clear what I'm doing. Times 6 meters is 18 kilonewtons per meter. Are we clear on that? On how I got that?
Yes.
because the live loading only acts on the top, not like, it doesn't really matter what this web width is, for example, right? That doesn't affect what the live loading is on top of the beam, right?
Yeah.
Okay, so now we have these loads. Are they factored or unfactored?
Unfactored.
Yes, very good. So what are our factors? Do you remember them?
Is this 1100? Yeah. Okay.
1170. Yeah.
1170. Yeah. Okay.
Do you remember them off the top of your head? What the load
1.2 and 1.35.
1.35G.
Oh, 1.35. 1.2
And for the 1.2, isn't it 1.5Q?
Yeah, so you mean 1.2G, right?
Yeah, 1.2G.
Very good. So basically we plug in those numbers. So G was 35.68. 35.68. This was 18. And the top number, even just like looking at these numbers before you calculate them, is obviously the bigger one, right? And we're taking the worst case loading scenario, right? So we're gonna continue with this one, the top one. So that's what our W star is. All right, so can we now chuck that in for our calculation, or is there something else we have to do? Right, I'll give you a hint. What's required in the next step is M star.
Then M star, according to your notes, there's two different ways, right? So this is an SSB or a continuous span.
Yes. So we're designing a continuous system.
So if it's continuous, then it's W star A squared over 8.
Oh, my bad. Okay, wait, I kind of screwed something up. It says the beams are simply supported. Yeah, you know what? Okay, basically what's happening is this. It's simply supported, which is this case, right? And in the standards, it says the flexural span's approximately the same length as L. But what it's saying in this question specifically is that the flexural span is 7,400 meters, millimeters, and the L is 8,000, right? So they're actually different numbers. It's just in the standards we can approximate it for a simply supported case, right? What I'm trying to say in the other one, in the case in my notes, I'll just scroll to where you were looking, Josh.
Mm-hmm.
We're talking about this.
Yeah, that's what I'm looking at.
Yeah, M star is equal to that if it's simply supported, and equal to that if it's continuous span. Basically, if the length and the flexural span are different numbers, right? Even if it's simply supported, I would still take A, which is the flexural span, because they explicitly give it to you.
Okay.
What we're trying to work out basically is what this M star value is, right? This M star, and it's more accurate. It'll give you a more accurate number if you give it if you input the flexural span, which is A. Does that make sense? So for that number, this is basically from solid mechanics. It's just it's just like the equation to find the bending moment of a simply supported beam. But there's a few differences. Oh, sorry. There's a few differences. The first is that you have to do the factored distributed load, which we've just calculated as 69.82. And the other thing is that for L, you should put in the flexural span. Right. Okay. So this is kind of important because the units are kind of important. Can someone tell me what the numbers should be for everything here? I might just pick on Josh, because I know you're kind of new to the whole load combination.
Yeah. So in this case, would it be? Are we looking for W star? Is that what you're asking?
I just want you to plug in W star and A, but
and
yeah,
the A
units and everything.
So we're using 69.82, right?
Yes, but which units are you using? That's the question.
The question is given in meters, is it not? Or are we, sorry, the flexural, that's in millimeters, is it not?
Yes. But do you
Okay.
want M star in so you can have M star in Newton millimeters or kilonewton meters. It's up to you, but you have to be consistent with what you give it.
Okay. So in this case, if I keep it as kilonewton meters, so that would be what, 69.8?
I'm trying to edge you to this little like trick. Basically,
Okay.
how do you convert kilonewton meters to kilonewtons per meter to newtons per millimeter? How do you do that?
Is it divide by a million or something? Is it divided by a million? No, it's divided by.
So how do you get kilonewtons to newtons?
I divide by 1,000.
And how do you get meters to millimeters?
Divided by. Wait, no. Times it by. Wait, I can't.
Also, sorry, this is times actually. Times by 1,000. Going that way.
Oh yeah, sorry, yeah. Times by 1,000.
Yeah.
Meters to millimeters. Times by that's 1,000 as well.
Yeah.
Yeah. So then it's just times by a million in total.
So what I'm trying to tell you is that this is both the kilonewtons per meter and newtons per millimeter. It's the same number.
Oh. Okay.
Yeah. For
All right.
W star at least.
Okay. So then 69.82, and we're using the flexural. Is that what you said?
Yes.
So 8 meters.
All right. I'm gonna plug this in. You want to do meters, yeah? So kilonewtons per meter.
Times by
and then
8 squared.
So 8 is the span. That's L.
Yeah.
But the flexural
span
so 7.4. Yeah.
Okay. And then divide that all by 8. So 477.92.
Yeah. So what units is that going to give you basically is what I'm trying to...
Meters squared, meters, kilonewton meters.
Very good. So again, it doesn't really matter what you kind of have this calc as long as you know which units it's going to be.
Okay.
That's what I was just trying to get across. So let's just keep it like this for now. Okay. So if everyone looks at the bloody notes, right? We go to the resizing formula. This is really important. Okay. This is probably the most unintuitive like fucking step out of all the steps. So I want to go through this really carefully. So I'm just gonna write down the formula first, right? This is the big mama formula basically. It did my fucking head in just revising for this basically.
So you ended up memorizing. Is this not on the formula sheet?
Oh, I didn't memorize this. I'm writing this from my other screen.
All right. Okay.
It is on my formula sheet. It's called the resizing formula in the design steps.
No. I mean, like in the actual.
Oh,
like
yes. So in the finals, you get to take home. So you get to bring in one-sided of handwritten notes. This is definitely on that. Yeah, there's no way else I can. But it might be on the cheat sheet, but I'm not too sure. I think I had to write it down though. So this is called the resizing formula. At least that's an unofficial name for it that I've just come up with, right? So I need you guys to help me plug in numbers. Specifically, these things which I've highlighted. Okay. So basically everything on the right hand side. So what are all these numbers?
I think the gamma, it was a bit up. It was like, it's 0.97 minus 0.0025 and FC.
Mm-hmm. So firstly, tell me what FC is. It's actually given in the question.
32,000 if we're doing in pascals.
Is that E?
Or is...
I think that's E. Wait, sorry. We want to keep it in MPa. Yeah.
Okay, cool.
Yeah, MPa is great for strength. Okay. So basically that instantly sorts that out, right? Can you also read out alpha 2 for me, please?
0.85 minus 0.0015 times 32.
Yes, so that's also a function of 30 of the compressive concrete, right?
Oh, is that like the common?
Oh, sorry. Like they'll give you 32 MPa, 25 MPa, 40 MPa concrete, all these kind of numbers. But it's always given in the question because you literally can't solve the question unless they give you FC. Anyway, so we have these numbers sorted. Thank you, Vina. Okay, Dom. How do we get these other values which we've highlighted in blue?
KU 0.25, right? I think from memory.
Yes. So we just assume this number. And remember, it's because it's ductile failure, right?
Yeah.
And the threshold is 0.36 for a ductile failure. So we're just doing well and truly under that threshold.
Yeah.
What does that mean for phi?
Sorry.
What does that mean regarding phi, the capacity reduction factor?
0.85, right?
Yes. So because we want to design a ductile section, not a brittle section, we take the ductility constant to be 0.25 and the reduction factor to be 0.85, right?
Okay.
Yeah.
Sorry, this is a stupid question, but would you ever design for a brittle section?
At least in this course, I know I was saying that I don't think it would really make sense. Maybe you can, like, if you're doing something that was like fairly, like you're not doing a building, for example, right? Say you're designing a pavement, maybe it will save a bit of costs to design a more brittle section.
Oh, okay, gotcha.
But I'm not sure if that would be flex. I'm not too sure, to be honest. In this course, we design like high stakes stuff like buildings and all that, and we always design ductile sections. Yeah.
Cool.
Okay. And then these other numbers here, these we've already got, right? This is just gamma again, KU again. KU is 0.25. This is 0.85. So KU over here is 0.25 as well. Okay, so M star, coming back to this, Josh, what number should I plug in for M star here?
478.
You sure, bro?
Yes, bruh.
So that's in kilonewton meters.
Yes.
Everything else has been in, this is MPa.
Okay.
The other ones are they're actually unitless. But MPa is basically newtons per millimeters.
Newton meters. Okay.
Squared, right?
Which is correct, right? In this case.
Yeah, no, it's correct. But we want to change the top so that it matches the units.
Oh, yeah.
Units. Yeah. So we can actually times this by 10 to the 6.
Mm-hmm.
So this times 10 to the 6 results in Newton millimeters. Right. Just so we're working the correct set of units. So it doesn't matter if you do it this way, Josh, by the way. As long as you convert it later. That's what I'm trying to tell you.
Okay.
Because we want all this stuff on the left in millimeters, right?
Okay.
Yeah. Okay. Last cooked thing. Justin, I'm gonna ask you this one. I'll just tell you ahead of time, we're designing for D, which is the effective depth. Remember, that's from the compressive fiber to the middle of the tensile bars, right?
Yeah.
That's what we actually want to solve for. But we still have this unknown B, right? So if you look through the notes, how do we convert B to D? Because we want a cubic, actually, for D, that we can just cube root.
Yes. You change B to 0.5D.
Perfect. So we assume 0.5D, right? Now we move that 0.5 to the other side, and we have D cubed, right, on the left-hand side, and we just cube root everything on the right-hand side that we've calculated for, right? So it would be like this, cube root, D cube root all this shit that we've calculated, and that gives us that D is 605 millimeters, right? Right? And you can do a sanity check. That means that the compressive steel is going to sit here. 605 mil, which seems about right, yeah. But basically now here's where it gets a little bit designery, a little bit consultant-y, because it's kind of stupid. Okay, basically we need to adjust D, big D, the total depth, right? That was previously 800 mil, right? We need to adjust that number, and so what we do is we say that it's equal to that value D, right? Plus the total cover, right? Which we always assume is 65 mil, right? Not always, but for beams with one layer of tensile reinforcement, we should assume that the cover is 65, basically, right? Okay, that means that we sub in 605 and we get a new value, right, which is 670. But here's where it gets even stupider, because we round up to a neat number. That's what they call it. I would say that means up to the nearest 50. So we actually take D as 700 mil. Okay, so now instead of 800, we've changed this to 700. Right? Are we following, everyone?
Yes.
And now we have to solve for B again, right? Because okay, basically if we go back to this shit, right? Let me duplicate it. So pretend that this right hand side equals something that we calculated, right? Instead of assuming, right, we can actually just plug in this value for D, which we've calculated as 605, move it to the right hand side, and we have B is greater than some number, right? And then here's where it gets even stupider again. We have to round that up to a nice number. For some reason, they rounded to 350. Don't ask me why. Is that the number you expecting in your head? Probably not.
So if you were to write 300 instead, that would be wrong.
Thing is, it's not wrong, because there's no wrong answers for this as long as it passes the check, right? If you were to write 300, you might barely fall under the capacity check. I'm assuming. I'm not too sure. Maybe it's fine, but for some reason the answers say 350.
Okay.
I'm so sorry. I don't know how to justify it, why they did this.
Fair enough.
This is
Why
designer
if
it's
bias.
350,
Sorry?
if it's 350, can we just assume 350 in every question we do now then? Because
No,
like
no.
you're gonna round up to that number anyways.
Okay, say you get 200. Are you gonna round to 350?
Okay, no, that's a bit far-fetched.
Yeah, so I can't give you a fucking rule of thumb. You know what I mean?
Yeah.
This is random. Like, as long as it passes the check in the end, it's okay. Basically, I would say 300 is not incorrect as long as it passes the check in the end. Yeah. But in the answers, we just follow the answers and we do what we're told. You know what I mean? Okay. Someone tell me the next step. Someone tell me the next step based on my little cheat sheet.
We tested that. Okay, so then recalculating M star with this new self weight.
Very good.
With the updated D and BW.
Very good. So what I'm trying to say is you find the self weight of this beam times the area of that, right? Times 25 kilonewtons per meter cubed. That is still the same tributary. What am I doing blue? Just to remind you. That is still 6 meters, right? That one is still the same slab depth. What we've changed now is basically how much of this rectangle exists, right? And so that's 0.35. This one is the overall depth, which was 700. So 0.7 minus that slab width, right? And then we find that area, right? Multiply it, and we get 31.55 kilonewtons per meter, right? WQ stays the same because that, again, this tributary width doesn't change, so it was just 3 times 6, right? And it stays as 3 times 6. Okay, all good. We do our load combinations. W star, it's that, and that. And the top one, which was 1.2G plus 1.5Q, is 64.86. So that's the updated number, right? Then we have to update our flex rule, our M star, pardon me. It's that. And yeah, all that. Plug the numbers in. Gives you 444 kilonewton meters instead, right? Okay, great. Okay, someone tell me what to do next after that.
Well, that's the end of the concrete thing based off of your steps. So now we go on to steel.
Yes, so now we're designing steel.
So we start with the initial sizing.
Okay. Yeah, so the initial sizing has this formula. Okay, can someone tell me what goes in this box? Sometimes this box is called J, and sometimes this box is also called X. This is
then
like
in this
an
case,
initial constant.
in this case, the box is dependent on what type of thing we are designing. So if this is a T-beam,
Yep.
it would be
There's two types of T-beams, right? That we can
there's
design.
a T-beam midspan and a T-beam.
So let's go back to the question.
Is it 0.95? If it's mid-spin?
Yes, so we're designing a T-beam, and we're designing it at the midspan.
Midspan, okay, so then it would be 0.95.
And this is going to inform quite a few of our next few decisions, the fact that it's a midspan design for a T-beam. So yeah, we plug in 0.95, yeah?
Mm-hmm.
M star is going to be this most recent value, right? The updated one, yeah?
Yep.
This is still going to be our ductile capacity, right? Can someone tell me what Fy and D are going to be? Fy can be found in the question. And D...
Steel yield.
Yes, so what's Fy?
500.
Very good. And what's D, lowercase d? We just calculated above. I might scroll up.
Sorry, what was 0.95 again? I didn't catch it.
Oh, sorry. So 0.95.
Was that a safety factor? Or was it?
Okay, I might scroll up to the notes here. If you want a name for this,
I'm sorry.
if you want a name for that box, or you can call it J or X, right? You can call it maybe a initial steel sizing constant. It's only used for initial steel sizing. Yeah. Okay, what's
okay.
What's
Steel
D?
sizing. Yeah. Thanks.
Sorry? What's lowercase d going to be when we plug it in?
605.
Very good. So we plug this in, 605. All right, this is going to give us... Give me a second. This is going to give us 1732 millimeters squared, right? Okay, so we don't do anything with this yet. All we're saying is that the steel has to be greater than this number, right? But this is an initial sizing. It's actually not going to be the value we're going to use when we're selecting our steel, right? We have to use this number to calculate the next value, which is gamma dn, which is the compressive steel, the compressive concrete depth, right? So if you remember, basically here's our T-beam. Say our neutral axis sits here, right? Say that's dn. We're doing this reduction factor gamma dn, right? So gamma is going to be a number less than 1. We're calculating what that is in order to... It might seem a bit unintuitive, but yeah, we need to calculate this compressive concrete region to calculate the steel, like how much steel we need. I guess it is intuitive in terms of this is how much steel it needs to be there to balance out this concrete. That's one way you can think of it. Okay, so this value is going to be AST times FY, alpha 2, FC, BEF. Is anyone confused on where any of these numbers might come from? I'm going to explain BEF in a second because I feel like it's the only one we haven't really talked about. But AST, we have from what we just calculated, we have FY.
From the question.
Yes, we've calculated alpha 2 previously. If you go up and these values don't change because they're a function of FC, right? So it's 0.8. And FC is given in the question, right? So the only thing we're going to need to calculate outright is BEF, right? So for a flange, that's equal to the web width plus 0.2a, right? Okay, so can you guys tell me, yeah, can someone tell me what these values would be? Justin, I'm going to pick on you.
I'm looking for BW.
Yep. So wait, I'll just show you here. So what's BW based on this drawing?
Is it? The 0.7 minus 0.18.
So that's
sorry.
the web
350.
Yes, that's the web width. Very good. So that's 350. What about A? What is A? A is a flexural span.
6.6.
Wait, say that again, sir.
6. Wait, is it 605 or is it 0.6?
Oh, sorry. So remember, this is center to center spacing. So it's the distance between beams. But what we care about here is the span. So in the long direction, right?
Oh, okay.
Okay, here's where it gets a little stupid, because effectively, this question tells us we have a simply supported beam like this, right? It tells us the flexural span is 7,400 mil, and it tells us the actual span is 8,000, right? And for BEF, our calculation of how much web width we have, it's a function of A, right? Which you'd think would be the flexural span, right? But guess what? We actually use 8,000 in the solutions. Because for some reason,
okay.
L overrides it. The fact that it's a simply supported beam overrides it here. So we use...
So that only applies to...
Sorry?
Sorry, that only applies to continuous then.
Basically, okay, here's one way to think of it. We used A when we were calculating M star, right, for the external loads. Agree?
Yep.
And that's that flexural span length, even though it's a simply supported beam. But now we're calculating the web width of the actual section. Now we use L for the now we override what the flexural span is, I guess.
Okay.
I don't know why.
It,
to be honest.
is it just to overcompensate, like to have something extra?
Oh,
Like, is there
yeah,
a reason?
that's a good way to think about it. Yeah, it will give us a bigger number for the web width. So yeah, that's good actually. That's a good. So yeah, you're right. If we took the smaller of those two numbers, would result in a smaller beam, right? We take the bigger number, we take on more of the slab width, and yeah, and then we have a stronger section. That's a good point. Shit. Okay. Anyway, my point is we take this as 8,000, which is the overall length. Okay. Yeah, that gives 1950. Right. Okay. Now we're doing something called the adjusted sizing formula. Okay. So we don't use that square anymore. We replace that square with essentially something a bit more accurate, which is to do with the concrete depth. Does anyone have any questions so far? Okay. Is anyone confused on where any of these numbers come from? So we'll just plug that in. Everything else is more or less the same.
Mm-hmm.
Except we take out that box number and we'll just replace it with an actual number, right? Okay, so this gives us 68 mil. Okay. Here we're going to do something which is utilizing this table. So we're going to select values based on the nominal areas in this table, right? Yeah, I need someone to tell me what they would select. This is fairly important. So you have basically $1,600 to play with, and you need to overspend it slightly. So how?
Slightly overspend.
Slightly overspend it.
Well,
That's
like
the minimum
3
you can
and
spend.
24.
Say that again.
And 24 3 bars.
So if you do 3
Oh,
bars,
sorry,
you underspend
slightly
it.
over. There's another one at N25 bars.
Pretend there's a credit card and you have to go over a certain amount of minimum purchase. You have to spend more than this amount, right?
N32 2 bars. Oh, so we have to go over.
Yes.
So, okay.
It can be by like a decent amount, to be honest.
N24 4 bars.
That's a good option.
1,800.
The solutions say 3 and 28.
3 and 28. Okay, so then why not just do N26 then? If that's the same number.
Oh, so 26 doesn't exist because these.
No, N20 6 bars.
Oh, I see.
Because that's another 1860.
Okay. I'm basically trying to drive a point across. Sorry, I'm trying to put across a point essentially. So the answer says this, yeah.
Yeah.
You said this one. And I think that's completely fair. I think there's nothing wrong with 4 and 24s. I think that's correct. I think the answers one's also correct, right? Another thing you could do, okay, well, maybe not for this number, but let's say that number was slightly lower. Let's say that was 1,580 or something. Someone could select that one, right?
Mm-hmm.
What do you think the problem is with going too low and too high? Like, what is just some thoughts you guys have? This is all theoretical. What the fuck? What was that? Vina, what do you reckon?
If you're going by the diameter,
Mhm.
I would say if you go to less, then does it affect the ductility? I'm just taking a wild guess.
Not really, because the ductility is based on the neutral axis, and that's based on cross-sectional area.
Oh, does
way.
it affect the M or the mu? Because it's like, never mind.
Oh no, okay, wait. Let me just draw this out. I think it would help. So, basically, the options are, let's say you do 6 N20s. Do you see what the problem with this is?
Oh, because when I had the 6 and 20s in mind, I thought it would be 3 on the top and 3 at the bottom.
Oh, right. No, we're just designing the tensile layer, so we only care about this.
Oh, okay. I completely missed that. I get it now.
Yeah. So
Oh,
it's
so then
actually
it's
too
just too
difficult
cramped
to
that
run
area.
over in this course how to do the compressive layer as well as the tensile layer for like designing a custom section. So they just do the tensile layer.
Oh, okay. Yep.
But did someone want to comment on that? Like, what's the problem with
Is it-
what is true?
Could it be over designing or under designing?
What do you mean by that?
Like over designing the section?
Over
Can I-
designing in terms of the strength?
I was thinking like, not sure if this is right, but if you have like, I don't know, N20s with 6 number of bars,
Yep.
maybe it constitutes towards more weight or like more material cost. Or if it can be more, I don't know,
I would say you're on the right track.
under designing.
There'd be more materials though, right? Like physically there'd be more materials.
Yeah.
Yeah.
There
Wait,
is basically. Yep. Sorry. I want someone else to say it, not me. So if someone has a guess.
Oh, yeah. From a construction, a tradie standpoint,
Yes.
being a foreman for over 20 years,
This is good. This is good.
when you pour the concrete, right,
Yes.
is it just the gaps in between,
Yes.
and then the ag will segregate?
Perfect.
Oh, I knew.
We call that congestion. We call that congestion. So if the
Yeah.
bars are too close together, exactly right, the fucking spacing between the bars is smaller, right? And there's spacing requirements so that the aggregate in the concrete can effectively flow through it. So there essentially is a bunch of spacing checks later that you'll see, which require the bars to be spaced far enough apart, right? So 6 N20s in a really like, and this is the web width, right? This is like 350 meters. That's not gonna fly. Like each one's only gonna have like 50 mil spacing, and then there could be like one big fat rock that's like 50 mil. It's like, you know what I mean? Like, you
Yeah.
get stuck in it. Anyway, what about going to? So we know that going too low in terms of diameter and having too many bars is bad. Why is too high bad as well? This is another construction kind of
This-
problem.
Is that too much space between it?
There's actually no regulation for having too much space as long as the cover is correct and the spacing is big enough.
Okay, so what was the thing? It was going too big or too small?
Going too big. What's the problem with going too big? Like two N32s, for example.
Oh, I remember you told me this. No, I don't.
I don't know if I've mentioned.
Or should I just give it a
before,
go?
to be honest.
I was thinking that, is it too much? No, okay, no.
It's just
Nice.
under
Thank you,
design, maybe.
guys.
I'll give you a hint. It is a construction issue. Like
Thank
it's
you.
it's a thing that designers might overlook, but people who have worked on site will probably have to think about pretty often.
Tradies getting back pain.
I'm not even kidding. You're on the right track.
Oh, really?
Yeah.
Oh,
It's
what?
physically hard to install and ship and stuff. Is it?
Yeah. So the weight of an N32 bar. An N32 bar looks like fucking that, whereas an N20 bar looks like that. These steel rods are really fucking heavy, right? N32s, I don't think I've ever seen an N32 on site, to be honest. it's really heavy, so it's harder for manual laborers to install it. Like you can install it with machinery and like more equipment and stuff, but it's just a lot more difficult, right? The other thing is that these straight bars are often bent on site. Like they keep straight bars because they're kind of if you
Universal.
order too many straight bars, it's fine. They can just be used for the next project. But sometimes these bars need to be bent into L bars or something, for example, like that. And N20s are relatively easy to bend, right? Even N24s are okay. Once you start reaching N28, N32, good luck fucking bending this. You know, like what they have to do is they get their like fucking steel cap boot and like use like bending moment and stuff to fucking bend it. But it's basically fucking impossible with this diameter, right? And the material properties and shit. So they avoid N32s where possible, essentially. Anyway, so yeah, I would say your answer, Josh, is good. The answers they provide though is they choose. Sorry, that was a big fat tangent, but have you got something out of that? They choose two N28s.
Okay, so just one other thing. So in the case that they've chosen the N28, and just as you said, it's a lot heavier.
Mm-hmm.
With this
Per
question,
per bar.
Oh, per bar, yeah. But since there's 3 bars, N28 in reality would not be the most optimal. Is that what you're trying to say?
Oh, no, N30. Sorry, N28s are relatively okay to handle. N32s is where it starts getting a bit difficult to install and stuff like that. No, you definitely can, and you'll see not in this course, but in like pre-stressed concrete and stuff, they'll use like N32s in like giant bridge girders and stuff, but they're not expecting it to purely be installed with like manual labor. These are usually precast installed in factories and stuff like that.
Okay.
Yeah. Okay, basically N32s. This will determine what the AST is. Wait, sorry, did someone say something?
Yeah, I got a deal.
Oh no!
Thank you. I'll see you tomorrow.
Yeah, thank you. See you, man. This governs what the area of the steel is, right? And that's it for our steel design. So we just have 2 more things. I'm not sure how much I'll actually run through it. I might just run through it theoretically rather than doing the exact calcs for it. They're basically just a bunch of tick OK checks. So I'll show you guys so that you guys can leave. Sorry, this is longer than I expected. I won't lie. So we've done all the concrete design and the steel design. Now we're doing something called design checks, right? And this is just checking that things are okay. This one I've visualized here, so it's to do with checking that the clear distance is okay. To be honest, this is not really in the scope of this question. What it's saying is if you're designing the actual spacing of the beams yourself as an engineer, but here they've provided the center to center spacing of the beams. So that's like the distance between these 2 beams essentially. You have to check that spacing between the beams is okay. Okay, the next one is the steel, the minimum steel requirement. This is a super AIDS looking formula for a relatively, like it's a long check, but it's not a difficult check. It's just plug and play. You've already got all these numbers, and it's just checking whether you've got it correct or not. So, do you remember how we were designing a T-beam at the midspan?
Mm-hmm.
All you have to check is plug in everything on the left-hand side, these unknowns, and then plug in everything on the right-hand side and make sure this left number is greater than the number on the right. That's it. It looks really AIDS, but it's really simple. Like in terms of the actual calcs.
Okay.
The other thing is checking. Oh, once you gather this is called the beam strength coefficient, right? So that's one check by itself, right? But then that left-hand side, that part there, that is slotted into this equation as well, and you have to do this other check to make sure that the steel is greater than some number for minimum steel. So this is called the minimum steel requirement. And that's the flexural tensile strength, which is what we've been talking about the last 2 weeks as well. Ductility requirements. So again, this is all dependent on what type of T-beam you're designing. So whether you're designing it at the mid-span or at the support, you chuck in BEF. Oh, sorry, this is an intermediate calculation. So it's to do with the fact that our neutral axis has changed slightly because we've adjusted AST, right? AST was that number has been updated to be whatever we've selected. So yeah, gamma dn changes slightly. You divide out gamma obviously to get dn, and then remember our ductility equation is this. Make sure it's less than some number. Our final strength check, right, is to make sure that the capacity, which you can get using this formula, is greater than m star, right? And then final detail checks as well. So this is again to do with what I was talking about: the clear spacing checks, the clear cover checks, making sure that the bars are far enough apart and far enough away from the edge so that they don't rust. Essentially, there's all these formulas for it. Yeah, I'll leave you guys to look through these, but there's 4 checks just for spacing, right? But they're really, really simple checks. They're just a little bit time consuming. And yeah, okay. Does anyone have any questions?
So how long ideally should this question take to complete?
Yeah.
The first time you do it, it'll probably take an hour. The second time
Yeah.
you do something like this, probably you can get it down to 30 minutes or so, or like third, fourth time, 30 minutes. Because like in the finals, there'll probably be 3 long calcs, right? And it's like a 2-hour.
Yeah, that's what I was wondering.
You want to try to squeeze it into 30 minutes or so.
30 minutes, okay. Yep.
And like it's just taking ages because you've never seen this before, right? But like even that first step, do you remember how like I was asking you guys, like what do I do, right? It takes a while even just to figure out what the first step is, right?
Yep.
But once you do it enough, you know what the first step is to find like the load combos and like the maximum moment, all that, right? Once you know what to do next, it doesn't take that long. It's just figuring out what the step-by-step should be. You know what I mean?
Yep.
You guys have any other questions?
I also had a random question. I remember from like previous workshops, we had M and M star.
What do you mean M and M star?
Like I'm pretty sure it was either M or mu, but the star meant that it was for design, and then M was like the normal.
Oh yeah.
And like yeah, so I was just wondering, like for this thing, we don't look at the. Okay, it's just the factored. Okay, got it.
Yeah. This is. I mean, you never really use this in design. This is
Yeah,
like
that's what I was
1300.
wondering.
Yeah. This is Eng 1300. And it's gonna be like your max moment for a simply supported beam, for example. So just to make it really simple, it's like this plus, and this is M star. Oh, sorry, this is just M max, right? This is a question which you can expect to see in 1300. Once you start doing design courses like steels, concrete, we care about the factored design moment because that's what's in AS1170. That's where you do like W star and worst case scenario kind of design basically.
Yep. Okay.
Yeah, this doesn't really take into account worst case scenario. This is just pure physics. It's not splitting up the loads into different type of real life types of loads like dead load, live load, that kind of stuff.
Yeah. Okay. Thank you.
All good. Does anyone else have questions?
No, sir.
Okay, all good. I'll stop recording then.